So now let's go on, continue discussing Klein's chapter 4. And so the next topic is section 4.3, constitutional isomers. And so this is actually going to be the first set of isomers that we've really discussed. Remember the conformers, going through the different positions of the molecules, those are not actually isomers because no bonds are broken. Those are interchanged, but just simply by rotation about carbon-carbon single bonds. Here, isomers, and this is your first type that we're going over, you have to have a bond broken in order to interconvert between true isomers. So here, these are constitutional isomers. They have different structures, but the same molecular formula. So this is a hexane. This is also a hexane. It's a branched hexane. And so there's a different connectivity. Notice this one has 1, 2, 3 CH3s. This one has 1, 2 CH3s inside the molecule. As the number of carbon atoms increases, the number of constitutional isomers increases also. And so you can see that this is in your table 4.4. This makes sense. And so, you can look over it. I don't think that you would ever be tested over something like that. But it is interesting, and you'll see that how these can get so much more complex rapidly by just increasing the number of carbons in the molecule slightly. You have to be able to recognize different structures as being either isomers or the same compound. So here, these are obviously two different isomers. We just discussed them. Here you have more branching. Here you have, so this branching is at the 2 position. Here it's at the 2 position. Here some's at the 2 position and the 3 position. These are all different compounds. Here the methyl is coming off of the 3 position. So this one is different than the other 4. But this one, notice 1, 2, 3, 4, 5. The methyl is coming off of the 3 position. So these two are the same. These two molecules are just really different conformers. And remember, those are not different isomers. This is just where you've had some rotation about a carbon-carbon bond. I guess what's happened is this methyl has rotated up and it was going down before. So these two are the same. I urge you to make your molecular models. If you don't see this easily, make your molecular models and rotate the ends around the carbon-carbon bond and look at them. If you can't see it, then you can actually name them. If they have the same name, then they're the same compound. The relative stability of isomeric alkanes. And so you can see that the what's happening here is in each of these are all being oxidized. Enough oxygen is provided to turn each of the carbons into CO2 and each of the protons into water. And so these are 1, 2, 3, 4, 5, 6, 7, 8. So these are all isomers of octane. And so they are, when oxidized, they are all going to go to 8 CO2 plus 9 H2O. So each of these goes to the same product. And so in separate reactions, it's possible to measure the amount of heat given off when each of these is oxidized or burned separately. And so this one gives off the most energy. And so then you know that this one had a higher energy to start with. And this one, the branched one, has the lowest energy. So that tells you that the branched alkanes are lower in energy than the straight chain alkanes. So branching decreases the energy of a compound generally. The things that you see true in the alkanes are going to be carried forward into alkenes, alkynes, alcohols, ketones, aldehydes, etc. These things that we're covering in alkanes are going to be true of the other families of compounds. Drawing Newman projections. Now, I urge you to look at the other video that I made. I had to go down to school to make that video using an overhead projector because it would be impossible to make it using this screen. And so what I'm saying here actually accompanies that video. That video is going to be essential in showing you how to use your molecular models and actually be able to see the different structures of these. These are going to be different conformers. These are called conformations again. So here, this is showing you how to draw it on flat paper. And so this drawing is the same as that drawing, and it's the same as that drawing. Notice that you've got a CH bond going up and a CH bond going down. Here you've got a CH bond going down and a CH bond going up on different carbons. And here you've got a CH bond going up and a CH bond going down. So these are all three the same conformations drawn in different ways. So here you can see this wedge. You've wedged that hydrogen back. You've wedged this hydrogen out at you. You've wedged that hydrogen back. You've wedged this hydrogen out at you. You can use, this is the wedge and dash drawing. You can use the sawhorse, and you can use the Newman projection. I think the Newman projection is most useful. That is, as I showed you in the first video that I made for you, where I was showing you the molecular models. What you do is you position the model in front of you so that you are looking down the carbon-carbon bond. And here you only have one carbon-carbon bond to look down. In other molecules, there might be a question of which carbon-carbon bond you look down, and you simply have to figure out which one you're interested in, which is the one that you need to single out to examine. And so these are Newman projections. They're ideal for comparing the relative stability of possible conformations resulting from the rotation. And this one, this particular Newman projection, this particular conformation, is the most stable of ethane because this is staggered. Notice the three hydrogens on the front carbon are exactly in between the three hydrogens on the back carbon, and so there is the least amount of repulsion between the electrons in the CH bonds in the back and the CH bonds in the front. The electrons are as far apart as possible, and electrons repel each other. So this is the most stable conformation. You're going to see other conformations in just a second. So I just finished telling you all of this. So this big circle represents the back carbon, and this intersection of lines here represents the front carbon. And these are the CH bonds coming off of that back carbon. You ought to get out, the other video I made for you and look at it carefully. The angle between the atoms here, this is a 60-degree angle. This is called the dihedral angle, or sometimes it's called torsional angle. So here, each of these is going to be 60. 60, 60, 60, 60, 60, 60. 60 times 6 is 360. Remember, there's 360 degrees in a circle, so that's pretty easy to figure out. That has to be 60 degrees. Now, as this rotates, this CH bond will eclipse that CH bond, and when it's actually eclipsing, the dihedral angle will go to 0. So, staggered conformations are more stable. That's what I just said a minute ago. Here, this is eclipsed. This is not shown quite as eclipsed. Here, the CH bond in back is supposed to be exactly overlapping the CH bond in front, but it's difficult to draw that on paper. So this might be confusing to you. Look at the video I made that has the models in it, and I show you there what is meant by eclipsed. So this is called torsional strain, where there is a tendency for there to be rotation about the carbon-carbon bond in the middle here in order to relieve this overlapping of the eclipsing of the CH bond in front with the CH bond in back in each of the three positions. And so the difference in energy between the staggered and the eclipsed is 12 kilojoules per mole. So here you can see the, let's trace this all the way around as the hydrogens in red rotate all the way around. So here first they rotate by 60 and they're eclipsed. Now they rotate by another 60 degrees and they're staggered. Then the front carbon, the front methyl rotates by another 60 degrees and they're eclipsed again. Then another 60 degrees, etc., etc., etc. You can see how much the rotation is. When it's gone all the way around, you can see this is 180 and it's back at the starting point. You can see the energy go up and down, up and down, up and down. This is 12 kilojoules. Each energy hill is 12 kilojoules because the staggered conformations are the same. There's a lot of symmetry in ethane, and so it makes sense that the eclipsed conformations have the same energy and the staggered conformations have the same energy. So this 12 kilojoule per mole is a relative energy. It's the difference in energy. And so that's attributed to, since there's 12, then it's calculated that each one of these eclipsing interactions costs 4 kilojoules per mole. Eclipsing of 2 CH bonds is 4 kilojoules per mole. Keep that in mind because we're going to have to use that number in a minute. 4 kilojoules per mole for 2 CH bonds to be eclipsing. This can also be explained, the stabilization of the staggered conformation can also be explained. I gave you the explanation that the CH bonds are as far apart as possible, and so that's stabilizing. It's also been proposed that there is some overlap between the electrons in the CH bond with this empty anti-bonding orbital. So there's some electron donation into the empty anti-bonding orbital. Personally, I think the other explanation makes more sense, at least to me. So now let's go back. Remember I said to keep that in your mind. The eclipsing of the CH bonds, like here, is 4 kilojoules. So in these eclipsed conformations, you can see this would cost 4 kilojoules. That would cost 4 kilojoules. The total here is 14. So here would be 4, here would be 4. That's 8. So what's left over is 6. So it's said that it's calculated that the eclipsing of a CH bond with a methyl substituent is worth 6. Okay, so it's 4 plus 4 plus 6 equals 14. 4 is 8 plus 6 is 14. And so this sort of a energy diagram is very common, and you've seen them before, I'm sure. And we will become much more familiar with them as the course proceeds. And so, this is calculating what I just said a minute ago, 4, 4, and 6. That's the calculation. And this is the end of the second part of Klein's chapter 4.